Okay, back to Lab 3. We had just fixed our obvious cert bugs by making sure that the getGuess function used the softmax function in order to make a valid probability distribution out of whatever parameters it had. And now we're going to work into numerical debugging. So remember, our goal here is that we wanted these proportions that we guess for box 0 and box 1 to match the true ones. Our true ones were farther up, but they were pretty evenly divided, a little bit offset one or the other. But these numbers that we learned, clearly way, way, way off. Like, what do you notice here? It looks like this one, um, for box 0, it just pushed everything all the way up into one single, um, like, it guessed that all of the beads were yellow. And again, we've got this really tiny number here. So this just doesn't seem right. So here's a kind of derived output. Sometimes it's helpful to look at the what does the raw parameters value look like? So what you tend to look at here is say, okay, these values are on really different scales. Here's a parameter that's plus 12 and minus 11. That looks wrong. So even if the output kind of was rationalizable, this just looks wrong. So now we need to figure out, how do we debug a numerical operation? So there's two big steps in numerical debugging. First of all, to check that your code is actually doing the thing that you think that you're doing. And second, to actually poke at any particular value and see why did that happen, to understand any particular phenomenon that you're seeing. And sometimes these processes go back and forth. So as we poke into a phenomenon, you realize something, that a step that we missed in the code or whatnot. Um, so let's see how we can debug what's going on here. So what are the things that we have available to us? We have the parameters. We have the guesses. We have this list of scores. Scores are all over the place. We also have the grad of params. So it's the gradient of parameters. So we can see what values it has. And we took a step in that direction. But, so you might have realized that we skipped a step here. After we ran this function again, ran this loop again, we didn't start out with our gradient being zeroed. It still has these numbers from last time we ran through. So this is stepping in an incorrect gradient. It's using the wrong gradient. It's just accumulating over several iterations. And sometimes that's actually what you want to do, but we weren't intending to do that. We need to make sure that we don't accidentally do gradient accumulation. So let's take our grad and zero it. So the next time we run through our training loop, we start with a 0 gradient, so that we actually get a valid estimate of what the gradient is for each parameter, for each loop. Okay, run that again. Still wacko wacko. So now we want to go ahead and check all of these lines one by one and just see, what are we doing. So in particular, these were kind of pretty well defined. We checked each one of these above. We didn't check any of these. So score.backward, we are looking at the end thing that we're trying to maximize here. So we want to make score go up, but then what's this line doing here? So this is our changing our parameters with respect to the gradient. Let's study this a little bit more carefully. What's going on? So we might have pattern matched too much to how things were in the book. We were always doing subtract the gradient, or something proportional to the gradient. But that was when we were trying to descend a loss. This is a score. So a higher score is good. So we want to change our parameters so that they give us a higher score, we want to be doing gradient ascent on our score. This is doing, that's with this minus, it's doing gradient descent. It's doing exactly what we told it to, but let's try actually gradient ascent on it by plus that gradient. So we're kind of hill climbing here. So let's flip this around. Now notice that we are initializing parameters again each time we run this code cell, so I don't really have to restart and run all. Okay, so we're ascending the gradient here. All right, now this looks a little bit better. Like something is going up sometimes, but still, this is major wacko here. So what can we do to figure out what's going on here? So first, let's look at these values. It looks like we got 0.5, 0.3, 0.1. That's kind of mimicking the true proportions, which if we look at was these were pretty even, and then this was a little bit less, but this is kind of amplifying the difference. And this second box is really different here, like 92% versus 0.03. It looks like it made the winner really take all here. Why would this happen? So you can stare at this for a while and think about the code, but really think about what are we rewarding? So one of the important takeaways of this is that a model will do exactly what we reward it to do. So we're rewarding this model for getting the highest mean score. Remember up here, we said that our score was defined by the mean of the probabilities that we gave to the right answer. Notice that this doesn't penalize very much, putting a 0 for a bead that we didn't see. Like um, if we put a 0% probability on seeing a red bead, but we saw a red bead, that should be really surprising. But this score function doesn't seem that surprised by it. It's just like, oh yeah, it could have been better, but whatever. It's just going to say, let's just push up the scores for the ones that we actually see a lot, because that's how we'll get a good score here. So it tends to do this behavior. It tends to push these numbers to the extremes. And in particular, it tends to want to do well for the majority case, totally at the expense of the minority, even the slight minority. So this is really underserving this minority group here, the red and the yellow beads in box 2, or sorry, in the second box. So this is it didn't look like a bad loss function, but this is a really discriminatory loss function, or our score function. It's really penalizing the minority here, and we wouldn't have been able to see that on sort of first principles, but if we saw our algorithm doing that, and we could verify that our algorithm does that, there's a couple of things that will change later, but it will still hold. This kind of loss function it only rewards the winners. It only rewards doing well at the majority. It does not care if we totally the minority. So we want a better loss function than this. Tune back in.